Greetings and welcome to lecture number 13 on external flow. This session we are going to discuss the numerical on flow over a flat surface. We already discussed the theory, how the boundary layer forms when the fluid flows over a flat surface, the characteristics of the boundary layers. Now this session we are going to discuss the numerical part on laminar flow or turbulent flow over a flat surface. So as far as the numericals are concerned, these are the expressions we supposed to use for solving numericals. These are the parameters need to be estimated in most of the numericals, and the expressions for laminar and turbulent flow. The first parameter, that is boundary layer thickness. So boundary layer thickness, it is given by phi x upon under root Rex, where x is the distance from the leading edge, and the corresponding boundary layer thickness is delta. So we can call this as a delta x as well. Reynolds number is the corresponding Reynolds number, that is Rux divided by nu, the formula we have to use. Because this is a Reynolds number at x. Reynolds number also varies from point to point. As the distance from the leading edge increases, Reynolds number increases. That is as per the theory, because Reynolds number is a function of x, and other two parameter, that is terminal velocity, mainstream velocity u and nu, these are the constants on most of the cases. This is the formula for turbulent flow for boundary layer thickness, which is 0.7371 x upon Rex raised to 1 by 5. Local drag coefficient, that is required for calculation of shear stress or frictional drag. So the formula is 0.664 under root Rex. And on the other side, this is the formula for turbulent flow. This is the average drag coefficient for laminar flow, and this is for turbulent flow. As far as the wall shear stress is concerned, for the average wall shear stress is estimated by using the average value of drag coefficient, CD into 1/2 rho u square, where in case of turbulent flow, the formula remains same, only the CD value of turbulent flow is used here. That is, it's a printing mistake, it's a CD value of turbulent flow. Similarly, the drag force, this only multiply this by area, that we can calculate the drag force. Here, multiply this by area, we get the drag force. So this drag force, it is called as the skin friction drag, or it is also called as a shear drag or frictional drag. So there are different types of drag forces that we already discussed. So mainly pressure drag or form drag, or this type of drag is called as a friction drag. So these are the expressions we supposed to use for solving various numericals. So depending upon the type of flow. So first thing, we have to recognize the type of flow, and accordingly we have to use the expressions. Now straight away we go to the numerical. So plate 25 meter long into 1.25 meter wide is moving under water at 1 meter per second. So this plate is moving, water is stationary. This situation generally arises when either boat or ship, when it is moving in a river or a lake water or sea water. So in that case, that surface of boat, whether it is horizontal or vertical, that we can treat as a flow or a flat surface. So similar situation we can correlate here. So this is a area of the plate is given. It is essentially the area which comes in contact with the surface that we have to consider. We have to calculate the distance x at which the laminar boundary layer exists at the leading edge, transform into turbulent boundary layers. So the critical length is asked. So where the laminar flow transforms into the turbulent flow. That is the first. Then the boundary layer thickness at the trailing edge. So here we consider x is equal to the length of the plate, and considering that, we can calculate the boundary layer thickness at the trailing edge. And finally, the drag force on two sides of the plates. Tech water is rho is equal to 1000 and nu is equal to 1 into 10 raised to minus 6. So these are the given quantities. Length of the plate 2.5 meter. Sorry, this is a printing which is 2.5 meter. Width of the plate is 1.25 meter. And the density of the water 1000 kg per meter cube. Kinematic viscosity 1 into 10 raised to minus 6 meters square per second. Velocity of the plate is given 1 meter per second. So here only we have to adjust this. Is instead of 25, it is 2.5 meter. So only procedure is important. Some values are maybe printing mistake. They are wrong, but you have to memorize the expressions or you have to memorize the methodology of solving problem. That is the key. The first thing we have to calculate the distance x from the leading edge and where the laminar flow transforms into the turbulent flow. So this is the case. This is the distance x where the laminar flow transforms into a turbulent flow. So this distance is called as a critical distance. So as per the nomenclature or as per the condition, the Reynolds number here or the critical Reynolds number is 5 into 10 raised to 5. It varies from 3 to 5, but we consider 5 into 10 raised to 5. So corresponding, so we have Reynolds number, critical Reynolds number, that is equal to U x critical divided by nu, that is equal to 5 into 10 raised to 5. So this condition we must know. So if we know this condition, velocity and kinematic viscosities are given. So we can calculate the critical length. So the total length of the plate, that is 2.5 meter. Its width, which is perpendicular to the board, it is 1.25 meter. So x, it comes 0.5 meters. So almost 20% is consumed for laminar flow, and remaining 80% flow is turbulent. Now at the trailing edge, obviously the length is 2.5 meter, where the flow is essentially a turbulent. So in order to calculate the boundary layer thickness at the trailing edge, we use the expression of delta for the rear end, that is 0.371 L upon REL raised to 1 by 5. So this expression we can use. Now in this expression, L is the length of the plate and Reynolds number is the corresponding Reynolds number. So where that is UL by nu. So for this length, that is 2.5 meter, the Reynolds number comes around 2.5 into 10 raised to 6. So after putting the values, we get the delta value. This is asked, that is the boundary layer thickness. So this is a boundary layer thickness at the trailing edge, that is 0.048 meter. Now we have to calculate the drag force on the two sides of the plates. Now in this case, both sides the boundary layer forms. So first we calculate the drag force on one side. So drag force, the total drag force, that is Fg, that is equal to drag force for laminar flow plus drag force for turbulent flow. As per the drag force for laminar force, the formula of drag force is CdA 1/2 rho u square, but 1/2 rho u square is common in both sides. But CdL and areas are different. This area, surface area is 0.5 into 1.25. That is the surface area for laminar flow. 80 is 2 meter. This distance is 2 meter. Remaining distance is 2 meter. And width remains same. That is 2.5 meter. So that we have. So CDL and CDT value we calculate by using respective expression. This is the expression for CDL. So most of the expressions of or expression of laminar flow, if you see that these expressions you have to memorize either by heart or logically. So this is 1.328 under root Rex critical. So Rex critical, that is for the entire length. So CDL value is coming around 1.88 into 10 to minus 3. CDT is 0.072 upon REL raised to 1 by 5. So CDT is 3.95 into 10 raised to 3. So putting these values, so rho is known to us, that is 1000, U is 1 meter per second. So after putting the values, So here REL is calculated by considering the length 2 meter, because this is a 2 meter length for the turbulent flow. So REL comes around 2 into 10 raised to 6. So by putting this value of REL here, we get this value. Then putting all the values in this expression, we get FD. So this is on one side. So the drag force on both sides of the plate is equal to 11 point, exactly double of this, multiply by 2. So it comes around 11 Newton. So this is a drag force on the both side of the plate. So this way we can use the expressions for solving the numerical on flow over a flat surface. Similar, the second numerical here, the streamlined train is 200-meter long with the typical cross section having a perimeter 9 meter above the wheels. If the kinematic viscosity of air at the prevailing temperature is 1.5 into 10 to minus 5 meters square per second, and the density is 1.24 kg per meter cube, determine the approximate surface drag or friction drag, we can say, of the train when running at 90 kilometers per hour. Make allowance for the fact that boundary layer changes from laminar to turbulent on the train surface. So here it is recommended that you consider the boundary layer formation, the entire boundary layer formation as a turbulent. Generally, if the speed increases, the length of the laminar boundary layer decreases. So if it is less than 10%, then we can neglect that particular length and we can apply the turbulent flow boundary layer for expressions for solving the numericals. So now first given quantities, here length of the train is given 200 meter. Typical cross section perimeter of the train, that is 9 meter. Then the surface area of the train, that is length into perimeter. So perimeter means considering the side, top, and both sides and top. That is a perimeter. So over entire the surface area, that is 1800 meters square. Kinematic viscosity is given, density is given, and well, free stream velocity as the train is moving. So the velocity of air we can consider, that is, if we are 90 kilometer per hour, convert it into a meter per second. So 90 into 1000 divided by 3600 to convert from kilometer per hour into meter per second. So these are the quantities given. Now we have to calculate the surface drag force. As per the equation, we have a approximate drag force. So first of all, we calculate the Reynolds number to check whether the flow is turbulent or not. So already it is mentioned, it is not necessary to check, but Reynolds number is required for solving. So first we calculate the Reynolds number. So it is well about 10 raised to 5, 5 into 10 raised to 5. Then we can say the flow is turbulent. Now we use the expression for CD, that is average coefficient for turbulent flow. So that is 0.072 REL raised to 1 by 5. Then we can, by putting the value of Reynolds number, we can calculate CD value. Then use the approximate friction drag over the train surface, that is CDA 1/2 rho U square. So we can calculate the drag. This is a frictional drag, that is FD is equal to 990.45 Newton. That is the answer. So this way we can calculate, this is a drag force, and then we can calculate what is the power required to, or what is the power consumed to overcome these drag forces. So it is recommended this drag force should be as minimum as possible. So it directly affects on the power. So almost if we multiply this by a velocity, so that gives the power, so which is a considerable value. So because the speed is high, that's why the drag force is considerable. Around 1000 Newton is a considerable value of drag force. So most of the then at the design stages, the efforts taken to minimize these powers by minimizing the edges, as far as possible, make the curvature and make the body streamlined. And this problem is related with the ship. The power required to drive the ship is given, that is 12 megawatt. So it's a considerable, as a very large power, that is 12,000 kilowatt. Power is required to cruise a passenger ship of 300-meter length and 12-meter depth at 40 kilometers per hour. If rho is equal to 1030 kg per meter cube, kinematic viscosity is given. Determine the combined form and wave resistance of the ship. So ship generally experiences the drag forces, form drag, friction drag, and at the same time, it also experiences the wave, because if it is traveling in a sea and during the high tide condition also, the wave resistance is considerable. So all these forces are involved. So now in this case, we have to calculate the combined form and wave resistance. So the total force exerted or experienced by the, that is a friction, form and wave in this particular cases. First of all, write the given data. Power is given, length of the ship is given, depth is given. So this is 12-meter depth. That is below the sea level, we can say. This is below sea level. So this is depth of this water, this 12-meter, we can say. 4 kilometer, 40 kilometer per hour, that we convert into meter per second, 11.11 meter per second. Density of the water is also given, 1030. Kinematic viscosity is given. Now we have to calculate again the drag force. So first of all, we'll calculate the total force, the total resistance we can calculate with the power. But first of all, we calculate the frictional drag. So combined waves, so Reynolds number we calculate for this Reynolds number. So for this speed, the Reynolds number is considerably high. That is 3.33 into 10⁹. Means for this Reynolds number, the flow is turbulent. Use the expression of CD for turbulent flow for calculation of CD. CD is estimated. Then use the expression of frictional drag, that is on both sides, because passenger ship. So there are two sides. You can say this side and other side. So the 2 multiplied by CDF A and half rho U square. So putting the values of CD area 300 into 12, density is 1030, and velocity is 11.11 meter per second. Putting the values, we can get the frictional drag, which is 410.52 kilonewton. Now this is a frictional drag, means around the skin or surface. But the power is given, and from the total power, we can calculate the total force that is experienced by the ship. That is 1080.1 Newton. So this force is equal to the friction drag plus form plus wave drag. We have to calculate this. We know this, so we can calculate the combined form and wave resistance, that is around 670 kilonewton. So this way we can analyze most of the end that is desired output we require, or desired in the investigations we require generally the drag forces or power required. This is we are doing this particular boundary layer theory for calculating the drag force, or consequently calculating the power required. That is actually the area of interest. So boundary layer thickness, all this formation we study. Finally, that we have to calculate this drag force. That's why we study this boundary layer formation or boundary layer theory. So this is about the So this way you can solve a number of numericals for practice also. So wherever there is a flat surface, so the key for solving problem, that is for using the various expressions, you can say. So if you memorize the various expressions that we already discussed in here, so all these expressions you have to memorize for solving numerical. This way you can most for laminar flow, the denominator is under root RE. For local, we use the value of x for calculating RE, that is ux by nu. And for average value, we use the entire length. As far as turbulent flow is concerned, we can the denominator in all expressions are same. That is RE raised to 1 by 5. Only you have to memorize the coefficients. These coefficients. Remember, there is x in the numerator only in boundary layer thickness. Drag forces, it is unitless quantity. So that's why nowhere there is x. Wall shear stress is formula is common in both sides. Only here the CD value of turbulent is taken and multiply this by area, that gives a frictional drag. So flow over a flat surface is especially analyzed to estimate the drag force, that is friction drag. So this way we can solve all the numericals. So I'll quickly go through all these numericals. So that's it from this session. At the end of this particular session, you will be able to calculate the boundary layer thickness for flow, whether it is laminar or turbulent, or a flat surface. So these expressions are only applicable when the flow is taking place over the flat surface. Calculation of drag coefficient or frictional drag or frictional power for flow over a flat surface. So with this, we have completed this session. Thank you very much.